All right, we are doing a grade 11 applied lesson on z-scores. So what the heck is a z-score? Well, for starters, quick recap. The normal distribution, which looks like this thing, let's see if I can just draw, let me just cut and paste this. The normal distribution is this shape here, right? And what do we know about this shape? It's the normal thing. What do you mean the normal thing? It's the normal thing. I'm trying to paste this here and it doesn't want me to. There we go. There we go. Move up you. There we go. Move up. That's close enough, I guess. And from there, what do we know about this thing? Well, we know that this part here is 34% of the data. This part here is another 34% of the data. Between one standard deviation on either side, you have 34%. You have 68% from here to here. Then the next one, it's called the 68, 95, 99.7 rule. So between here and here, you have 95% of the data. So do the math. That's another 13.5% in that column, and another 13.5% on this column. Then between here and here, between three standard deviations left and right, is 99.7% of the data. That's another 2.35% of the data here, and 2.35% of the data here. And then finally, this little bit on either side is 0.15%. And remember that it does go on forever, right? You could have 4 and 5 and 6 standard deviations left and right, but that's such a small percent of the normal distribution that it's altogether it only counts to be to the left and right 0.15% each. So this is again my 68, 95, 99.7 rule. That's how normal distributions behave. But here's the problem. What if I'm dealing with a number that isn't exactly one of these lines? Suppose I had a standard deviation that was like 1.2 instead of exactly 1 standard deviation away. What percent of the population is 1.5 standard deviations over? How do we figure stuff like that out? We do it by counting something called a z-score. Now, first of all, normal distributions can have any mean you want, but a normal distribution that's a dot for my eye. A normal distribution that has a mean of 0 and a standard deviation of 1 is called a standard normal distribution. So it's a standard normal distribution if it has a standard deviation of 1 and a mean of 0.
So what's the difference between a normal distribution and a standard normal distribution?
Well, a normal distribution can have any mean you want, right? Like look at the example we just had, right? What was the, we were doing one where the mean turned out to be 72.25. And the example before that, the mean turned out to be 104.5. On a standard normal distribution, the mean is 0, and the standard deviation is 1. Z-score is a standardized value that indicates the number of standard deviations of a data value you have above or below the mean. So z-score, a standardized value that indicates the number of standard deviations of a data value above or below the mean. So how many standard deviations are you? Now, if you have, hey, I have 68% of the data, well, then I know I'm plus or minus 1 standard deviation. What if you were 72% of the data? How many standard deviations are you? Well, it's 1 and a bit. How do I figure out the bit? How do I find those numbers between these beautiful symmetrical bars here? That's where we have something called a z-score. The z-score is how many you have, and the z-score, you have some room under these notes on your page, right? I organized my page here a little differently. So in the room you have below there, here's the formula for z-score. The z-score formula is z equals x minus mu over sigma, where again, z is the z-score. And you should know what the other data points, or what the other variables stand for. X stands for just a data value. Mu is, of course, my mean. And sigma is, again, my standard deviation. So that's our new, and I'm happy to say our last formula for this chapter. Okay. So let's take a look at this example. This is a very common thing that you have to use statistics to do. Question? Yeah, like a single value from my, the question is, does x mean one data value? Because we did have that other formula, we had to use all the data values. Remember we had a sum, which means we're using them all and then adding them up. This one's just for one data point. So yes, x stands for one data value. Good question. Okay, let's look at this example. This is the kind of thing we use statistics for all the time. Two candidates for a scholarship have taken different tests that are equally reputable, but they have different means and different standard deviations. Their results may be compared by considering the z-scores. Madeline scored 205 on a test where the mean was 190 and the standard deviation was 8. Sarah scored 91 on a test that has a mean score of 81 and a standard deviation of 4. Who has the better score? So these two students are trying to get into a university and you are the admissions officer. Which one do you let in? Who's the better student? You might go, well, 205 sounds more impressive than 91, but is it better compared to the rest of the class? Already some people are shaking their heads saying they think Sarah might be the better student here. Is that a guess, or can you kind of look at it and sort of see it? There you go. I like the way, the person, you probably can't hear this in the microphone, but somebody's already saying, well, there's less of a spread when you look at Sarah's score. I like the way you're thinking. Let's calculate the z-scores. So the z-score for Madeline is, let's use our new formula. It's x minus mu, right, over sigma. So x minus mu over sigma. So for Madeline, her z-score is, she got 190, that's her data point, minus the standard deviation. Wait a minute, have I got that upside down? I do, oops, I put that upside down. See, this is why I have to look up formulas. I never remember them very good. X minus mu over sigma, that's better, thank you. So 190 minus, what was her class's average? Oh, sorry, I've got the number wrong. Madeline scored 205, that's better. Her class average was 190. She's definitely above the class average, and the standard deviation is 8. Do the math on that, and you get, what do you get? You get 1.875. So where would she be on a curve? Let's make a curve for Madeline. So they have a diagram underneath for yours, right? So for Madeline, her z-score is 1.875. Her data has a mean of 190. Mean falls right in the middle, right? The standard deviation is 8. So this line is 1 standard deviation. It's 198. This is 2 standard deviations. It's 206. This one would be 182. And this one would be 174, right? Because we're counting downward by 8s. Where is she? She is 1.8. So this is 1 standard deviation, this is 2. 1.85 would be maybe around there. because her score was 205. So maybe I made that line too fat. I don't like that line. Let's make a skinnier line. 205 would be very close to 206. So there's 205. And again, it's not 2 standard deviations to the right, it's only 1.875. And that means that all of the people in this curve, and again, I'm bad at coloring, I apologize for that. All the people that I just shaded there are below her. What percent of the population is that? I don't know. We're going to learn how to figure that out. But let's compare this to Sarah. So Sarah has a z-score of, she scored 91, the mean was 81, and the standard deviation was 4. That gives her a standard deviation of a z-score of 2.5. Now what's better here, a higher z-score or a lower? Or in this case, it's a higher, because she's farther from her mean than Madeline is. And we can see that on the graph. For Sarah, her z-score is 2.5. So remember, this puts her, that's the mean, that's 1 standard deviation over. She is 2.5. So let's put the actual numbers on it, like we did for Madeline. The mean on this data was 81, and the standard deviation was 4. So that's the 85, that's the 89, that's the 93. Her score was a z-score of 2.5, which puts her at 91. Where's 91 on this graph? Exactly halfway between 89 and 93. So she's right here, right? So she has this much of the population behind her. So who is the better student compared to their own classes? Even though 205 looks like a more impressive score, people who were shaking their heads and saying, no, Sarah looks like the more impressive student here, you are right. So I'm going to put this into words. You have some room under this graph, right? Sarah is the better student here, I should say here. I mean, I don't know. This is just one subject. Okay, let me finish this. Her score is farther to the right, farther from her classes. Is that how you possessify class? Farther from her classes mean than Madeline. And another thing you can say is more of Sarah's competition, right? Her classmates. I know it's weird to think of your classmates as your competition, but at the university level, that's very much true. More of Sarah's competition did worse than she did when compared to Madeline. All right, we have a couple hands up. Question?
How do we know what the lines are on the
How do we know what the lines are on the graph?
Yes.
Well, because remember, this is how the normal distribution works. This line here, let me use red. This line is your mean. This is 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. They tell us that the mean is 190 and the standard deviation is 8. So I was just counting. 190 plus 8, plus 8, plus 8. This one, the mean was 81 and the standard deviation was 4. So starting here at 81, plus 4, plus 4, plus 4. And as you can see, Sarah's got more of her class worse than Madeline does. Question? Her z-score is higher? Yes. The question is, if you didn't hear it at home, is if this was a question on the test, can't we just say Sarah's the better student because she has the better z-score? Yes. If I was to ask a more specific question, like, in this case, why is a better z-score an indication of a better student? You'd say something along the lines of, because it means more of her classmates did worse than her, or she did better than more of her classmates than Madeline did. See the logic on that? I guess you could even say, because she's further right on the graph. That's true. I'd give that a mark. That's a good answer, actually. Because Sarah's further to the right on the graph. She's further into the normal distribution. But you know what I kind of want to know here? What I kind of want to know is exactly what percent is this? If she was right on the line, we could calculate that. We did that all day long in the first part of normal distribution, right? We know that up to here is 50%. Between here and here is 68. So if you were up to this line, if you were just all of the data, if you landed right on this line with your score, 50 plus 34, you just beat 84% of your students, of your classmates. If you go to here, what's 84 plus another, what was this one again? Plus another 13.5. You just beat 97.5% if you made it to this line. But she didn't quite make it to that line. What percent is it? That's what we're going to learn how to calculate tomorrow. So we'll cut it there. We'll pick it up there tomorrow. Okay? So I'll stop the video, and we'll pick it up right there tomorrow.